Okay, Assalamualaikum. We're going to continue with the final chapter and the final topic, interfacing communication. Okay, so direct memory access. Okay, so the last way, okay, the what you call it, the the final discussion, okay, based on our previous topic, is direct memory access. So what is direct memory access? Is method transferring data from the computer RAM to another part of the computer without processing it using the CPU. That means we skip the CPU process. Okay, so this is example when we try to transfer data from our thumb drive into our hard disk, okay, or vice versa. While most data that is input or output from your computer is processed by the CPU, some data does not require processing or can be processed by another device. DMA can save processing time and is a more efficient way to move data from computer memory to other devices. So required condition for DMA. The I/O interface and memory must be connected. So it will be connected through I/O module. The I/O module must be capable of reading and writing to memory. Conflict between the CPU and the I/O module must be avoided. Okay, that means you have to try to avoid simultaneously copying data from thumb drive to hard disk and hard disk to thumb drive at the same time. Okay, so interrupt required for completion to release back the DMA. Okay. Sound card may need to access data stored in, this is the example, the sound card may need to access data stored in the computer RAM, but since it can process the data itself, it may use DMA by passing the CPU. Okay. Video card that support DMA can also access the system memory and process graphic without needing the CPU. So that's why some video card or graphic card come with their own processor, so they can manipulate data themselves. So same goes to sound card. Okay, the sound card, or you can call it, let's say, in the old days, okay, when you are using a PC, okay, there's a play button at the CD-ROM. Okay, so CD-ROM drive. So you can simply put what you call that, the audio CD inside the inside the CD-ROM drive, and straight away press the play button instead of running it using a software inside a computer. So the instruction, application program request, I/O service from operating system, privileged program I/O instructions. Okay, to initiate direct memory access, program I/O is used to send the following information: location of data on I/O device, the starting location in memory, the size of the block, whether you want to read or to write. Interrupt to CPU. Later, when it's done, we will send an interrupt to CPU to notify the CPU that DMA have completed function. So this is how it happened. Okay. Okay. So CPU set up a device such as a disk drive for DMA transfer and disable DMA interrupt. Okay. So that means in order to start a DMA transfer, CPU must first initiate. Okay. So that means CPU has to set up the device. Okay. So data is transmitted into DMA. Okay. So data is transmitted into DMA. Okay, while the CPU is free to handle other tasks. Okay, so that means while you are transferring file or data from thumb drive to hard disk, CPU can do other tasks. Okay. So once the data transfer is completed, the CPU is interrupted. Okay, so we send the interrupt to the CPU to allow it to handle cleanup after DMA transfer. That means to notify the CPU the transfer is complete, so please close the file and so on. Okay. So the next discussion is about bus. Okay, so previously discussed why we call it a bus, because it sends three data. Okay, so the data is data bus, okay, address bus, and also control bus. So aside from that, there's another line, we call it as power, but it may or may not be in the bus itself. Okay. So what is a bus? A bus is a group of electrical or optical conductor for carrying signal from one location to another via a conductor printed on circuit board or line. Each conductor in the bus. Okay. So bus characteristic: number of separate conductor. Okay. Bus also data with it bits carried simultaneously, addressing capacity. Line on the bus are for a single type of signal or share. Throughput, okay, data transfer rate in bit per second. Distance between two endpoint, okay. Number and type of attachment supported. Type of control required. Feature and capabilities. So there are two kind of bus. Okay, so one is parallel and one is serial. Okay, so a parallel bus, okay, it has high throughput. Okay, that because all bit offered are transmitted simultaneously. That means we transfer what you call it. Since we transfer bit, okay, 16 bit at the same time. Okay, so we can transfer it here it is one, okay, so zero here, zero here, zero here, so let's say we end with one. Okay, so it's kind of expensive and required a lot of space, generally used for short distance. Okay, so that such as from CPU bus, such as CPU buses and on computer motherboard. That means everything connected to CPU usually we use parallel because it's much more faster. Okay, and then serial bus transmit one bit at a time. Okay, so that's mean even though you want to transmit the same data, okay, what happen is it send one. Okay, send one first, then send another one, then send another one, then send another one, then only send zero, 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 one. One bit at a time. Single data line pair and a few control line. For many applications, throughput is higher than for parallel, okay, because of the lack of electrical interference. Okay, so this also doesn't relate with DNA. Okay, so this is a discussion about direction of transmission. Okay, so basically, but we previously discussed in the example of handshake, which is full duplex. That's mean full duplex mean bidirectional simultaneously. Okay, that's mean the sender and the receiver can communicate at the same time, just like a telephone. Okay, so half duplex means only uh, one point can talk at the time. That means if the sender is sending data, the receiver cannot send any data to the sender. Okay, like walkie-talkie. Okay, the full duplex is like a telephone. Okay, so simplex unidirectional is like a radio or tele. Okay, only the television center or the radio station can send a signal to our device. So method of interconnection. Okay, so when we connect something, there are basically two for this because this not considering the network. Okay, so it can be either point to point, okay, or single source to single destination, or multi-point bus, also broadcast bus or multi-drop bus. Okay, so cable is mostly used in point to point buses that connect to an external device. For point to point, we can say that like our remote. Okay, when you want to switch the channel of a television, it's a point to point connection using the infrared. Okay. Hmm. Yeah. For multi-point, okay, connect multiple point to another point at the same time. Okay, so this based on the picture, this is we can say like the computer in our lab. All the computer in our lab, okay, all the nodes of computer in our lab is connected using a single bus. Okay, which is our we connect it using our switches. Okay, or inside the computer itself, the CPU, okay, the disk controller, the video controller, the memory is connected through the bus in our system, which is usually printed on the motherboard. Okay, point to point versus multi point. Okay, so plug-in devices. Okay, so usually a serial port a device, okay, connected using a modem, or a straight connection inside the CPU from the control unit to the ALU. Okay, in a broadcast bus, okay, for example, they are using the Ethernet, okay, where the computer in our lab is connected using a switch. Okay, or this one is our CPU, all the what you call, all the element on the motherboard connected to the motherboard is connected using the bus on the motherboard. So stack. Okay. So previously we also discussed stack when we discussed about interrupt. Okay. So the use of stack. Okay. Used by CPU to store information from register temporarily. So basically, stack is there. The stack is there, and the stack is usually empty. The stack is used. Okay. When previously when we discussed about interrupt, when program A data. Okay. When we want to interrupt program A that is not completed yet, okay, so what will happen is the data inside program A, okay, the data inside the register, the program counter of program A will be stored temporarily inside the stack, so that program B data can be transferred into the register and also the program counter to start program. This is because there is a limited number of registers inside the CPU. The two main register to access the stack is uh, stack and the stack pointer. Okay. So type of stack, there are two type of stack. One is hardware stack, where a number of registers are set aside within the processor to serve as the stack location, or a software stack, where an area inside the CPU, okay, we will empty some part of the CPU that will be later used as our stack. Okay, there are advantage and disadvantages of this these two type of stack. Okay, so the advantage of hardware stack is you can access it much more faster because the stack is inside the register of the CPU itself. Okay, but the advantage is, as we know, okay, the CPU is so small and it has limited number of register. So if you use the stack inside the register inside the CPU as stack, okay, it will reduce amount of register that we can use inside the CPU itself. Okay, the advantage of software stack is the size. Okay, the size is not limited. It's only as limit as our memory, our RAM. Okay? But the disadvantage is it will cause our program to slow, to what you call it, to slow the access time. Okay, because the stack is not within the CPU. The stack is on the main memory. So you need to access the memory, main memory much more frequent. Function and usage. Okay, so stack, when we use stack, okay, as previously discussed, okay, stack is used mostly in interrupt. Okay, stack can also used in a subroutine. Okay, so that means if your program is calling another program. Okay, so when stack okay, when stack instruction occur, okay, or to store data when the most recent use data will also be the first needed. So that's mean sometimes your register get too congested. Okay, there's so much data you keep updating inside your register, but there are more data you need to put inside the register and your register is full. So some of the data, instead of being transferred into your main memory, it will be transferred into the stack of your inside the CPU. Okay. So stack is an efficient way of storing intermediate data value during complex calculation. Okay. So stack operation of stack. Okay. So the stack address is built one byte at a time, similar to the memory of operation. So, but we need to remember. Okay. So stack work in a last in first out algorithm. That means the first data you put will be at the bottom. Okay, so this is the first data, and then you will stack. That's why we call it a stack. So this is the second data, the third data, the fourth data. So when you want to retrieve the data, you must pop it by the stack. Okay, so the last byte put on the stack will be the first byte retrieved from the stack. Okay, so normally for a stack instruction inside what you call that assembly language, we will use the push, okay, to store data inside the stack, okay, and pop to retrieve data from the stack. So once we pop, okay, the data inside the stack will be deleted or will be ignored. Okay, so stack pointer, okay, the job of stack pointer is very critical when push and pop are performed. So stack pointer, okay, will store the current what you call it, the current location where the last value is stored. Okay, so it will force us to store at the next value. So the stack pointer point to the top of the stack, which is not empty. Okay, stack pointer incremented when data is popped off the stack. Oh, this one is okay. Oh, okay. It is right. Okay, based on the Indian. Okay, stack pointer will be decremented. Okay, so why they said will be what the stack pointer will be incremented? Okay, it is because they are using the what you call this. The addressing is using the this one is using the big Indian. Okay, Indian. So that's mean the register. Okay, the memory start from big small address, okay, small address to the bigger address, but the stack pointer, okay, the stack pointer is pointing here, so that means the data is stored from the bottom up, bottom up, bottom up. Okay, so let's see. Okay, so let's assume this is the data inside our register. Current stack pointer is showing at 1236. Okay, this is the current stack pointer. Okay, 1236. Okay, and then we have ax, bx, and bx value. 24, b6, 8, 5, 6, 2, 6, c2, 5, f9, 3. And we want to push ax, bx, dx. That means we want to put data into our stack. So stack start from the bottom. Okay, so now the address is 1236. So when you push ax, so the 24 will be stored at location 1235. Okay, so when we say only instead of all 4 digits store, okay, only 2 digits store, because we have to remember we are assuming that every block of the memory can only save 1 byte. Okay, 1 byte means there are only 8 bits. Okay, so 2 means 0 0 0 0010. Okay, 4 means 0010. Okay, 4 means 0010, and then 4 means 0100. Okay, so we can only store 8 bit or 1 byte at any memory location. Okay, so when we push ax 24 b6, so 24 will be stored at the bottom since it go in first, and then only will be stored b6. Okay, and then the next one we push what we call that bx 85 c2. So 85 will go here, 85 will go here, and c2 will go here, and then push cx, which is 5f93. Okay, so let's say, so this the final stack pointer, okay, will be showing at 1230. Okay, okay, given the following stack, okay, so the stack start af, the stack pointer is at a18fa. Okay, so this is the current stack pointer. Okay, so that means if you want to pop this stack is usually the stack is built following the little Indian method. Okay, so this one is based. Okay, see the difference. Okay, This is based on big Indian. Okay, the address start from the smallest address to a bigger address. The next example is showing based on what do we call this? Based on the little Indian. That means the address. Okay. Oh, sorry. So the address of the stack is based on this one is based on little Indian. Okay. Ah yes. This one is based on little Indian. Okay. So the address is start at so when you pop CX, okay, so what will happen is you are getting the whole stack. So this 2 byte is one data. So that means you will push and you will pop and store inside CX, okay, the value of 142 should, okay, and then you pop DX, that means you pop another 2 byte, okay. So when you pop another 2 byte, so it will be 2C, okay, 2C 6B, okay, and then you pop another 2 byte, okay, it will be F691, okay. Okay, Little Indian and Big Indian. So Little Indian method, okay, so the high bit goes to the high address and the low bit go to the low address, okay. The Big Indian, the low bit go to the high address, the high bit go to the low address, okay. So is the difference between Intel and also the Motorola. Most Intel, okay, use Little Indian, and Motorola or what you call it, Apple technology use Big Indian. This is why we previously also discussed that we cannot simply install program built for Windows inside an Apple product and buy this, because the way they address they access the address of the memory is different. Okay. To further discuss about the big Indian and little Indian, okay, if we can see here, it's quite confusing. Okay, so if you see our memory module, okay, it is built on the uh, big Indian characteristic from small address to the bigger address. Okay, so when we have a big Indian memory module, okay, that means our stack will be built using the little Indian method, because the address will start from the bottom up. Okay, to further understand this, okay, we need to understand this one. Okay, so let's say we draw this one first. Okay, so we have a processor of Intel, okay, and the Motorola. Motorola. Okay, so we know that the Intel will use the big Indian. Okay, sorry, the Intel will use the little Indian. Okay, while Motorola will use the big Indian. Okay, so for Motorola, the address will start from 0 until F F F F. Okay, okay, that means the address will start from the smaller address to the bigger address. Okay, but for Little Indian, the Intel, okay, the address will start from FFF to a smaller address, which is 000. Okay. So that's the main difference between Intel and Motorola or Apple technology. Okay, so that's the first one. Okay, so that's how the addressing will go. Mm, so that's the first thing you need to understand. Okay. So since the in Motorola, in Intel, they use the little Indian. That means the what you call it, from the bigger address to the smaller address. Okay, so that means the stack. Okay, the stack in Intel We'll use little, we'll use big Indian. Okay, because the stack will start from the bottom up. Okay, that means we start from a smaller address to a bigger address. Okay, and for Motorola, okay, the stack, okay, in Motorola will use little Indian. So by understanding this, then only we can answer the next question. Okay. So given this problem, okay. So given this problem, given this problem, okay. So the first thing, say for this one, okay, and oops, okay. So let's discuss this first. Okay. So let's discuss this first. So let's say the what you call it, the stack pointer. Okay, the stack pointer. Okay, this one is showing the address of 2000. So 2000. Okay, so arrange the width in the stack using big Indian. Okay, so that means our stack. Okay, big Indian from the smaller address to the bigger address. Okay, so that means the 2000 is somewhere around here. So we know that we are using the big in what you call that, uh, the big Indian. So that's mean the net address will be 2001, 2002, okay, and 2002. Okay. So the stack itself, we are talking about the stack. We are not talking about the memory model. We are talking about the stack. Okay. And 2004. So this happened to the, okay. So this is the stack pointer. Okay. So let's see, color it yellow. Okay. So this is the stack pointer. So the first thing we move AX. Okay. So in our AX, we move 1, 2, 3, 4. Okay. And in our BX register, we move 9A, BC. Okay. And then we start to push BX. So we push the first value 9A, BC. So what will happen here is, okay, 9A. So what will happen here is 9A, 9A will be stored here, and then BC will be stored here. Next one we say push AX. So AX value is 1, 1, 2, and 3, 4. Okay, okay. So that's mean the first one is now our stack pointer will be updated to uh, 2002. Okay, and then the final value of our stack pointer, okay, will be 2004. Okay, so let's try to arrange this in a stack in Motorola, which use big Indian memory, okay, big Indian memory address. So this will cause our stack to be in little India. That means the address start from bigger number to a smaller number. So that means, okay, 2000 will be somewhere around here. So the smaller number, okay, the smaller address will be 1 FF. EF, E, okay, and then 1 F, F, A, B, C, D, okay, E, E, F, C, 1 F, F, C, okay. So this is our current stack pointer. This case is the same, okay. So the stack, our stack pointer, okay. So our stack pointer start at 2000. The starting point is still the same. So this is our current stack pointer. So the first thing, same one, okay, we push AX with the value of 1, 2, 3, 4, and then we push BX with the value of 9A, B, C. Okay. So what happened when we push bx? So bx, okay, bx value 9a and bc. So thus this will change our stack pointer from 2000 to 1 FFE. Okay. Okay. So the next one we will push ax. Okay. So when we push ax, we will make our stack pointer to become 1, 2, 3, 4. Okay. So by doing this, what will happen is our stack pointer will finally be addressed at the what you call that, 1 FFC. Okay. So let's try to do it side by side. Okay. So in this, you can see that we can spot the different here. Okay. So stack the stack in Intel will be using big Indian stacking. The address will start from a bigger address to a smaller address. Okay? But the stack in Motorola will bypass the Motorola addressing module. Okay? So in Motorola they use big Indian. That means the address start from 0 to FF. Okay? But the stack will be the other way around. So stack in Motorola will be in little Indian. So the address will be from a big one to a smaller one because the stack will always start at the bottom. Okay, so that's how we can see it. Okay. Okay, so for the last example, okay, given the question here, so first we need to observe the input. Okay, so when we push AX with a value of F6, so basically we will be pushing, okay, there will be a 0 at the front because it has to be in a word, okay, a word which is 16 byte. Okay, so there is a 0 at the front. So for all the value is 1 byte, you have to change it to 2 byte. So that's the first thing you need to do so that our stack will be equally distributed. And then, okay, so you need to observe the sequence, the byte being used in the push instruction. Okay, so if you we will only cater where the byte is, the bit is 1. Okay, so for the bit is 0, we will ignore. So that means we will ignore the x. Okay, and for the next thing, so we look further into the question. Draw the content. Uh, draw the content of the stack with related address after the interrupt occur, following a sequence of PC. Okay. So that means the first one, they want PC. This one will be PC. Later it will be AX. And then this is the sequence. And then CX. And then BX. And lastly BX. Okay. So since we uh, want to put this to store this, okay, we want to store this into the stack. Okay, so all the instruction will be push. Okay, so this one will be push. Oh, this will be push. Okay, and then the stack pointer. Okay, we start at FF00. Okay, so we have to bear in mind stack pointer. What is SP? Okay, so SP is equal to stack pointer. Okay, so what does stack pointer mean? So stack pointer, okay, so stack pointer basically means what is stack pointer basically means the, how we say, the last and the last address with a meaningful input data. Okay. So we look back at the sequence just now. Okay. Look back at the sequence just now. So we will see that dx input is 0. Okay. So when input, so this is 1. So okay. This one is 0. This one is 1. So for the 0, okay, for the 0, it will be ignored. Okay. So that means we are not catering for 0 value. We will not be catering for the 0. Okay. So what will happen with our stack? So the current address of our stack is ff00. So let's say this is our stack ff00. So further up it will be fe. Okay, fe d fe c e f d f e f e e e c d e f. Okay, nice. And then f e e sorry f 9. Okay, f e f 8. Okay, so let's stop there. So next level, this is the last value. There is a value there. So we will not be using that location. Okay. So the first one we want to push the value of PC. Okay. So the value of PC is 2602. Okay. And then the value of AX 00 F6. Okay. And then the value of BX 0082. Okay. So BX will be ignored. The value of BX is 0082. Okay. 0082. Okay. 0082. Okay, and this will be sorry. This one will be 0082. Well, this one will be CX is 3624. So EX is equal. Let's check again. 2602. This one is 00. Sorry, 006. Okay, this one will be CX. CX will be 3624. Okay, and then the value of BX 008. So we push this one. Okay, so the value will go here 2602. Sorry, 2602. And then this one will be 00 F6. And the next one will be 3624. Okay, and then 0. What's the next value? The last value will be 008. Okay. So from here, you can see that the value. Okay. So our stack pointer have changed from this one. Okay. to the new value of uh, f e f e. Okay, so that's how you answer this kind of question. Okay, you have to observe the byte sequence. Okay, you will ignore the zero. Okay, but the sequence of the push instruction will be based on the question. Okay, so why we need a stack to store the current interrupt. So I think that's all for this chapter. Thank you.